In this video, we're going to get a precise understanding of what truth functional means, and especially why would a connective be considered a truth functional connective. I know we've already talked about this, but now that we've got a lot more logic under our belts, we can get like a definite understanding of exactly what's going on. Now, when you read 3.5 in our text, there are a couple of sentences there that can seem a little mystical. So I thought first thing I would do is sort of break down a couple of those sentences there, especially the key concepts in them. The first is the one that says, consider the set of truth values, the set that includes T and F, true and false. First, I should say that a lot of the concepts that you're going to see are made familiar in math. So if you see something from that seems familiar from math, like I think I remember that one, then probably the ideas are going to be very analogous. So you should know that the word set is very important in math, and set really just means a collection of things. Although I think even calling it a collection is a little bit confusing. You could think about a set sort of like a list, and absolutely anything you want to can go on that list. I can list off the numbers 1 through 10. I can list off the different kinds of dogs. I can list off this phone, this glass, and this pencil. And the only thing that makes lists different is what's on those lists. So if you have anything extra, or if you're missing anything, totally different set of things. So for example, if I had the numbers 1 through 9, that would be a different set than 1 through 10. 1 through 11 would also be a different set. Or pencil and cup would be a different set than pencil, cup, and phone. Pencil, cup, phone, and book would be a different set. That's what a set is. So our list, our set, is only going to have two things on it: the truth values, true and false. And speaking of value, that's another important concept here, again, that we've already talked about. A value is basically something that you can assign to some other thing. So for example, in math, we often assign number values to variables. I can assign the number value 3 to the variable x, or I can assign the number value 4 to the variable x. And in the case of math, there are as many values as there are numbers. So there are a potentially infinite number of values. In classical logic, however, we're only going to be using two different values, true and false. And we're going to assign these values to propositions. So consider a proposition, call it proposition P. P acts like the variable x in math. True and false act like the number values in math. I can assign the truth value true to P, or I can assign the truth value false to P. The next mystical sentence here is that one that says functions on this set. Right? That sounds just a weird way it's a weird locution, right? A weird way of saying something. But that word function is another important concept in math and in logic. And a function basically takes an input and assigns it exactly one output. So here's a bizarre example. Imagine the set of fruits: apple, banana, orange, and pear. Now pretend you work at a fruit exchange. Your job is to take the fruit that the customer gives you and exchange it with a different kind of fruit. But there's a specific set of rules about exactly how this is going to go down. The customer gives you an apple, you are to give them an orange. Give you a banana, you're going to give them an apple. They give you an orange, you give them a pear. They give you a pear, you give them a banana. Now, this set of rules about how we're going to exchange the fruit, this is a function. It takes an input and tells you exactly what the output should be. And we can say that it is a function on this set of fruits. Again, that weird way of saying things. But it's not the only function you could have. Exchange an apple with an orange, exchange a banana with a pear, exchange an orange with an apple, exchange a pear with a banana. So notice, to make a new function, I didn't change the inputs here. What I changed were the outputs that would come from the inputs. Here's another one. Apple to pear, banana to apple, orange to orange, pear to banana. Now, you probably noticed the weird one here was orange to orange, but you can do that. You can have an input and have as your rule just assign it that same value for an output. Here's another one. Apple to orange, banana to orange, orange to pear, pear to banana. Now, notice the weird thing about this one. Two of our inputs have the same output. That's okay. What we really want are rules that tell us to go from one input and tell us, like, what output am I supposed to give out here? That's all we really want. What's really important then is that we don't have one input and multiple outputs, right? We want our rules to tell us, definitely when you get this input, give this output. So if one of our rules were get an apple, give an orange or a banana, well, that's not gonna cut it, right? We can't be going to two different outputs and not sure which one we're supposed to go to. We want one specific output. So that wouldn't be a function. But the ones before him, those were all functions. Just rules for taking an input from the set and giving each one a specific output. And we could name each set of rules. We can name each function, and probably to keep things straight, we would just want to like number them, right? Function number 1, function number 2, or something like that. So there's our fruit function. Now I'm going to take kind of a risk here and assume that you know enough math that this next illustration will be helpful, but not so much that this is going to be incredibly boring. But there are also functions in math. So for example, consider the expression x squared. This is a function because I can assign different number of values to that variable x as inputs, and it will assign number of values as outputs for the expression. So for example, I assign the number of value 2 to that variable x, and remember x squared just means x times x, that's all a squared means. So our function here will assign the number of value 4 to the expression, or I assign it the number of value 3, and our function here will assign the expression the number of value 9. Because 3 times 3 is 9. Notice it's cleaner than my fruit functions here, right? This function is just like one statement, whereas my fruit function, I had to delineate every single input and tell you every single output. This function is really nice and sweet because it can take an infinite number of value inputs and it will tell you for each one exactly what you're supposed to do. And in math, we have a really sweet way of denoting this, right? With that f of x, that was the function of x. So f of x equals x squared. That means x squared is a function of the value that you assign to x. Assign a value 3 to x, and we can see we would write that f of 3 equals 3 squared. F of 3 equals 9. So one function in math is f of x equals x squared. We've defined that function as just being that x squared. Another function we could have, f of x equals x cubed. Again, takes a number value input, tells you exactly what kind of output you're going to get. You're going to get x times x times x. So whatever number that is, you multiply it by itself 3 times. In both our functions here, we have the same set of inputs, but we have different outputs. And that's what makes these two different functions. Now in math, when you have two different functions, typically you'll name one f of x and the other one g of x or something like that. But we could also just number them like we did the fruit functions if we really wanted to. And then finally, we have truth functions, what we're really interested in. As we said, we only have 2 truth values, t and f. And think about a function that you could make with just these 2 truth values. You would need to be able to take each input and say what the output should be. So here's a possible function. Every time we get the input of the value t, we assign the value f. Every time we get the input of the value f, we assign the value t. That's one way of taking the inputs and telling us what kind of outputs we could have. Here's another one. Well, every time you get a t, you assign a t. Every time you get an f, you assign a t. And since we have 2 inputs and 2 possible outputs for each input, we would have 4 different possible functions here. Now, just like our fruit function, we can name each one of these functions just so we know what we're talking about. But we don't want to name stuff like Steve and Kevin, so let's use like an f to symbolize function, and then we'll just number each one of these guys so that we know which one we're talking about. I put on these like a number 1 at the top, by the way. The superscript is 1. I'll explain that in just a second here, but for now, the subscript, the 1 and 2, that's what we'll name them. F1 or F2, that'll be the function name. So notice we have an input, which is a set of truth values. Each input is assigned 1 output. So each one of these is a function on the set of truth values. These are then truth functions. And that is exactly what it is to be a truth function. Now, looking at these different functions, you may recognize one of them. The function that takes t as an input and makes f the output, or takes f as an input and makes t the output, that's the same function that we use to define our connective not. It's the truth table we had for it. So in our text, Nicholas Smith, our author, notes that by giving the truth table for this connective not, we did 2 things. First, we picked out one of these 4 possible truth functions. Second, we made that the meaning of our connective not. In other words, not, that little sign there, that little neg sign, just means this function right here. And that is what it means to be a truth functional connective. A connective that is defined by the truth function that we chose for it. Now, not was kind of a weird connective because it was the only one-place connective. The rest of the 4 connectives are all 2-place connectives. So for our not, we had a truth value input, 1 truth value input, and a truth value output. But when it comes to these 2-place connectives, we're actually getting 2 truth value inputs. So for example, in the OR connective, we get an alpha or beta. Well, we have one input, which is the truth value for alpha, one input, which is the truth value for beta. Those are two different input truth values at the same time. What are we going to do? No problem. We'll take as the input the ordered pair of those two. So the parentheses that you'll see, that's to say that, hey, these two things inside the parentheses, it matters what order we take them in. Otherwise, if the first proposition were true and the second one were false, it would be the same thing as if the first one were false and the second one were true. We don't necessarily want that. So our input is still just truth values. It's just they're coming at us in pairs, and we care what order they show up in. Now, there are 4 different possible combinations of truth values. So there are 4 different possible inputs. So our truth functions are going to be a little bit bigger for these guys than they were for the one-place connectives. But for each input, we still only have 2 possible outputs. That means we have 4 times 2 different combinations that we could have. We have 8 different truth functions for two-place connectives. But by the way, we could have truth pairs for outputs. We could do that, but that's not going to be very helpful for us. What we really want is to go from the 2 truth values of our inputs, right? The 2 truth values for the propositions that make up the complex proposition, like for example, alpha and beta from alpha or beta. And then we want as an output a truth value for that whole complex proposition. And we only want one truth value for that whole thing. So we're going to only want outputs of T or F, but not ordered pairs of outputs. So here are the 3 different examples of truth functions for two-place inputs that the book gives. Do any of them look familiar? Pause the video and see if you can figure out if any of these are the truth functional connectives that we've been working with. Well, one is if and only if. Why? Because an if and only if proposition is true when either both propositions that make it go into it are both true or both of them are false. So if our input is TT or our input is FF, we're going to get an output of T. But if our input is TF or FT, then we're going to get an output of F. Also, number 3 is an OR. Remember, for our disjunction, the rule was if any of the disjuncts are true, then the whole thing is true. The only time it's false is if both disjuncts are false. So if we have an FF as an input, we'll have an F as an output. Everything else will have a T as an output. Now, just like we named the one-place functions, we'll also name all the two-place functions. And here's where that 1 at that superscript is going to come into play. When you see a 1 for the superscript, one-place connective. When you see a 2 in the superscript, that will pick the ordered pair of truth values for their input. Now, let's talk a little bit about the way that the book writes out all this stuff. Whenever you see the brackets and then you see a proposition inside, those brackets will stand for the truth value of that proposition. So the truth value of alpha or beta is identical to, it's defined as function F3 for the two-place function that takes in the input of the truth value of alpha and the truth value of beta in that order. Or for the if and only if, the truth value of alpha, if and only if beta is defined as function F1 for a two-place connective that takes for its input the truth value of alpha and the truth value of beta in that order. Now, that's how we're defining these connectives. That's what those connectives mean. That's the only thing that they mean. That is what it means to be a truth functional connective. Now, you may wonder, what in the world is the point of that? Why are we making such a stringent case for defining these connectives as truth functional? Well, when we're thinking about what we're doing in logic, it might be confusing. It might seem like we're discovering something here. It might seem like there's this thing, negation, and we discovered what its meaning really is, and then we apply it in this logical course. But the problem is this: language and logic don't always overlap in this isomorphic way. So, for example, the word not in English. It's not always the exact negation in logic. For example, we've seen before, you can use it sarcastically. I could say, yeah, this shirt is not pink. And what I actually mean is that this shirt is pink. So the not there isn't really a logical negation. It's actually the opposite of it. And notice how there can be disagreement in English about exactly what that not means. I can say, yeah, that shirt's not pink. And then you say, oh, but you were being sarcastic, right? I'm like, no, I was colorblind, right? And so we can argue, well, did you really mean not, or did that mean, the opposite of not, or whatever? So if we're defining our negation off of the English word not, and that's it, then we're going to have this headache of debating exactly what that not meant. Instead, here's what we're doing. we're going to look at all these truth functions and pick out the truth function that closest resembles the way that we use that word in English or whatever language you speak. But we're still going to keep them separate. We're going to define our connectives using this truth function. And then when we speak in natural language, then we're going to have to translate our natural language into logic. We're going to keep the logic nice and pristine so we know exactly how it's working. The real debate's going to be going from the natural language into the logic. What exactly do we mean by this sentence, and how do we fit that into the logical system? But once we got into the logical system, the great thing is, since we've defined these connectives by this truth function, we're not going to have to worry about any kind of debates such as, what does this negation mean in this logical statement right here? We'll be able to save that headache for natural language, and we'll have this nice and clean system of logic that we can use whenever we want. So that's really the idea behind focusing on truth functional definitions for these connectives. Okay, anyway, let's go on to 3.5.1 exercises. Number 1 says this: can the meaning of any of our two-place connectives and or if then or if and only if be specified as the truth function f2 for two places defined in figure 3.2. So that one was that if you get a true, you get a false, false, you get a false, true, you get a true, false, you get a false. Now, you should really just look at all the different truth tables that you have for all of our 4 connectives and see if any of them match that one. That's how you'll be able to figure out the answer to this one. Now, we've already said that function 1 and function 3 are if and only if and or. So we know that if and only if and or can't be those two. So you just want to check your conditional truth functional table and your conjunction one. And when we check those two out, it doesn't look like either of those overlap with this function 2 here. Number 2 says define truth functions f4 and f5 such that the meanings of and if then respectively can be specified as these truth functions. So for and, we know that that's supposed to be true only when both conjuncts are true, otherwise it's false. So in that first row where you have the TT, the output should also be a T. In all the other rows, the output should be an F. Whereas for the if then, the conditional, whenever you have a true antecedent and a false consequent, then you're going to have a false conditional, everything else will be true. So in row 2, your output should be F. For all the other rows, your output should be T. Number 3 says, suppose we introduce a new one-place connective star and specify its meaning as the truth function F1 defined in figure 3.2. What is the truth value of star A when A is T? Well, when A is T, we said, looking back at function 1, we said that the output for a T is a T, right? So the input for is A there is true. Then given that F1, our output should be true. Number 4 says, what truth values do you need to know to determine the truth value of star if A then B? Do you need to know both, just A but not B, just B but not A, or neither one of these? So normally you would have to know both of them. But when you look back at that function, F1, both outputs are true. So it really doesn't matter what the truth value of if A then B is. If it's true, output's going to be true. If it's false, output's going to be true. So you don't need to know either one. Answer is 4. And finally, number 5, which of our connectives could have as its meaning specified as the two-place function g of xy defined as follows? G of xy is function 3, where the inputs for function 3 is function 2 of x and y. So let's see, function 2 is the negation function, right? So that would mean whatever the truth value of x is, then you'd have to flip the t's and the f. So if x is true, then we're going to have a false for f2. f3 is the disjunction function. So first let's see what happens when x and y are both true. When x is true, plugging it into function 2 is going to make it false. Y is going to be true, so we're going to have a false true. Function 3 says if we have a false true, then the output is going to be a true. So whenever we have x is true, y is true, then our output is going to be true. When x is true but y is false, that function 2 is going to swap the t's and f's. So we're going to have a false for function 3, right? And then function 3 is the disjunction. So that means that if you have a false, the whole thing is going to be false. So when x is true, y is false, then our output is going to be a false. When we have x is false, y is true, function 2 is going to make that x to a true. So we're going to have a true true for function 3. And for disjunction, true true means the whole thing is true. So when x is false, y is true, we have a true output. And then finally, when x is false, y is false, again, function 2 is going to make that into a true. So now we have a true false for function 3. And in function 3, if you have a true false, your output is a true. So for x is false, y is false, we have a true. So now we have true true, output true. True false, output false. False true, output true. False false, output true. That is exactly the truth function of the conditional. And I believe we define that as function 5. So yeah, truth function 5 would be this g of xy. That last one was an interesting one. I actually like that one a lot. Anyway, that is all for chapter 3. The only one thing, note 6 was a little bit interesting. If you like, I can make a video on that one too, but otherwise, we will move on to chapter 4. For next time, please read chapter 4.1. So anyway, I'll see you in the next chapter.